In today's session for AI agents, we'll be learning how to implement function calling and how to provide image inputs to our LLM. And also we'll be understanding what different model parameters are available. This model parameters enables us to get precise outputs, tune the model responses. So it is also important while building AI agents. So we'll also be understanding and learning these parameters. So first, what is function calling? So a function calling is nothing but you are giving a tool or a function to the large language model so that it can execute it automatically to get the result. Like when you open ChatGPT and give it a prompt like my install dash dash software on my system, so then it asks you what system is you're using, then you type the system name. So in function calling, what the LLM will do is, instead of asking you for what system it's your system is, it will directly execute a command so that it can get the output and it will exactly know what your operating system is. So instead of relying on human input every time, it will automatically execute the function to get the result. Also, functions enable the LLM to connect to various cloud APIs, get latest information. So overall, it helps us in better understanding the context. For creating AI agents, functions are the most important. Context and functions are most important in AI agents. So in this session, we'll be understanding what are function calls. So in function calling, we can define multiple tools. This is only one tool. In such schema, we can define multiple tools. There the model can decide which function to call exactly and with what parameters to call. So the model can decide if it has to call one specific function or two functions. We can also call functions in parallel. So this is the advantage of function calling. So how we can do function calling in LangChain? First, the default thing, you have to import LangChain. You have to import OS for getting the model and API key parameters from the env value. We are using .env to load the env values. Here we are defining the language model using the chat OpenAI interface. As in this session, we are using Gemini models, not the OpenAI models, as OpenAI models are priced. So we have to define custom base URL. Then we have to define tool. So how can you define tool? So LangChain provides a good abstraction with which we can define tool. For that, we have to import a tool from LangChain tools, from LangChain core.tools. So now I want to ask my system. I will give a tool like through which it can get my system information, and I will return this information for the language model to see. So now I will ask my system, how can I install a certain package? Like I want to install NeoVim. So how can I install this package? Provide me the command to install NeoVim on my system. So first we have to import this human message. Now I can prompt my LLM. First, we have to provide the LLM, bind the tools with the LLM. So for that, LangChain provides us with the bind tools method, bind tools. And then we have to invoke the messages that we can print the response. You see, an LLM doesn't have an idea what the function does, what kind of input it takes, what output it provides. So it doesn't have any idea. So how we can give the LLM the information about this function? For that, we will use the docstring. So docstring is basically, it provides us the information about what the function does. You can provide the docstring in them, triple quotes. Fetch the current operating system information. So now we'll try running it. So yeah, you can see here it called a tool. So I guess you have to, you see, the LLM didn't call the function in the first two runs. So we have to provide proper description to our tools, because otherwise it won't understand what the tool is used for. So now we have provided a proper information. It called the tool successfully. So you can see in tool calls, it called the get system info, because it doesn't have any arguments. There are no arguments here. So this is how you can do tool calling in LLMs. Now you can see how we can provide this result back to the system. So the LangChain provides us a template. So what you can, the tool node, what it provides. We don't need to do all of this by ourselves. Tool node directly does all of this for us. We just have to provide it with the tools. Then if a tool call is available, we just pass. The tool node requires in a specific format. We have to give it in like messages. Then we'll provide the response to it. So now you'll see what it does. To see, it automatically provided us with the content, name, tool call ID. It directly filled those fields for us without doing it manually. So it helps us in coding. Now we have to just append this response. As messages is a list, we can extend it. Then we'll call our LLM again. We have to add the response from the first LLM to the messages so that it can understand that it called the tool. You can see first it calls an LLM, then it calls the tool. Didn't call it now. And then it provides us the tool response. Now we can call the LLM. You can see it provides us with the response to install NeoVim on your Ubuntu 24 LTS system. The most straightforward method is to use apt. It directly gave us the command sudo apt install NeoVim. So this is how tool calling is useful. So now I will go through the code once again so that you can get a better idea. So we used chat OpenAI from LangChain to call the Gemini model. We used .env to load the environment variables. From LangChain tools, we you imported tool to define our functions. Then we used human message from LangChain messages. We used pretty print so that we can get colored output in the terminal. And from LangGraph, which is an AI agent library, which we'll be focusing on later, it provides us with a template of tool node, which makes it easier to call the tools. You can call them manually, but manually sometimes we miss one or two fields and get an error. So instead of that, we can directly utilize this tool node that they provided us. Then we defined our LLM, which was chat OpenAI. We used our Gemini model, and for that we defined the base URL, which is provided by the Gemini model, which uses OpenAI compatibility. Then here we defined our tool. So now for now this is just a static tool which just provides us with the information. To make it more useful in all the systems, we can use system.run to run the command and get the output from the std out directly and get this response. For now, to make it simple, I just use statically typed here. Then for messages, our first message was to provide us with the command to install NeoVim. And we used human message because LLM expects our messages in a certain format, which I told before. It expects the system message or human message. So we used a human message. Then we bind the tools with our LLM so that the LLM can know that it has these tools available with it, that it can call. Then we gave it the get system information tool. Then we invoke with the messages. Then whatever response the LLM gave us, we appended it to the messages so that the LLM can have a history of what response it had, what queries and responses it gave. So we need to append it to the messages. Messages is kind of the memory or history for the LLM. Then we defined our tool node. For that we gave you imported the tool node from LangGraph and gave it the tools. Then we checked if the tool call is there in our response from the AI. We response.tool calls. If there is a tool call, then we invoked it using the tool node. Tool node expects to get the tool responses in a specific format like messages and then a list of the list message. Then we appended the response from the tool node into our LLM history. Then we provided the entire history to the language model. The language model then analyzed our output, which is this system information. It came to know that we are using Ubuntu 24 LTS. Then it gave us the command that it's sudo apt install NeoVim. You can check the command directly again. You can check if it's running. So you can see that it directly gave us the command, open your terminal, run the command sudo apt install NeoVim. So in this way, using function calling, you can define the functions and provide dynamic context to our LLM. Image inputs. So we can provide our LLM with image data. So the Gemini model which we'll be using, it can understand text, image, audio, etc. file format. So we can provide the LLM, pass the LLM the image information. So how can we pass that? LLM cannot directly understand the image. So first we have to encode it using base 64 and then provide it in this given format. So using this format, we can provide the image information directly to the LLM. We can also directly provide the URL, which when we directly provide the URL, the server encodes the image automatically. We don't have to handle ourselves that, but sometimes the server fails to encode the image data. So it will be better if we can directly encode it on a system. So I will not be demonstrating this now. I will be directly giving you the code in the GitHub repository because it's pretty easy. It's not that difficult. I will move forward to the most important part, that is the model parameters. So how to guide our LLM responses? For that, we have various model parameters. Like temperature is there, top P, top K. So these parameters are used to define our model response. So in our previous lecture, someone asked me a doubt like what is the difference between logits and probability values. So, so what is temperature? So the temperature parameter influences the creativity. It increases the randomness. Uh, it like determines if you want the responses to be deterministic or more probabilistic. So how does it do that? So as I said in the previous session, the LLM classifies the tokens using softmax function. So what softmax does it takes the logit values, that is the uh, values outputted by the model, and converts them into probability values. These probability values are then used to select the best tokens. That is, the tokens which are higher probabilities will be chosen first. Now, how does the setting temperature makes a difference? So you can see in the softmax, normal softmax, and the difference between after temperature was applied. So you can see that temperature parameter influences softmax function, like it divides the z value. So how does it actually make a difference? How we can visualize it? So you can see here the logit values for each of these tokens like donut, cake, apple juice, book. Before setting temperature, that is a temperature equals to 1 means it doesn't make any difference because dividing by 1 its values itself. So at temperature 1 we can see that donut has the highest probability, cake has a little bit less probability, apple has a higher probability than cake, then juice, then book has almost negligible probability. Now, what happens if we increase the temperature, that is, decrease the temperature to 1.5? You can see that the probability of donut actually decreased a little bit. Probability of cake increased a little bit. Apple decreased, juice increased, and book it increased a lot. So what it tries to do is it tries to equalize the different probability values. If we set temperature 0.1, you can see that donut, which first had a higher probability, now it has like close to 1 probability value. So if a token has a probability, higher probability close to 1, and if we set a temperature, lower temperature value, then it makes sure that only that token will be selected. It increases the probability value of the most probable token. So in this way it can influence our output. Now if we change our temperature to like something like 1.5 or 2, it will try to equalize the probability value. So in this way, you can tell the LLM to be more creative or be more deterministic. I only want a specific response. So like this. So temperature is used to define um, controller output. Now top P. What is top P? So top P sets the cumulative probability value. Like the output tokens like donut, cake, apple, juice we have. So each token has a probability. Donut has a 0.3, cake has 0.2, apple has 0.2, 0.5. So like this. Now if we set a top p value of like 0.8, so what it will take try to do is only select those first tokens whose probability values add up to 0.8. You can see here it will take like donut, cake and apple. It will take these three tokens and discard these remaining two tokens because the cumulative probability value of these highest value tokens adds up to 8.8. So in this way, top P helps to select only the highest occurring probability tokens. Now, generally using both temperature and top P together are not advised because uh, they essentially do both, try to do the same thing. So we avoid using both the values at the same time. Also top P is a relatively simple method. It selects the top n tokens. Like if you set top k to 5, it will select the top 5 highest probability token. Top k equals to 1 will only select the most probable token. And now top k is deprecated and top p was introduced. In some latest models, top p is also deprecated. Only temperature is provided, temperature parameter. So in this way, using temperature, top P and top K, we can influence our model responses. Anyone has any doubts in the model parameters? So local LLMs, how to set up a local LLM? For local LLM, there are various tools like LM Studio, Olama, VLLM. I had provided you with a guide where I told you to install LM Studio. LM Studio basically provides us with local LLM to run so that we can test our agents or software. So LM Studio runs on an llama.cpp backend. Llama CPP backend has a lot of hardware support, like it supports CPU and GPUs like Intel, Nvidia, AMD, even Apple GPUs. It supports a lot of hardware. And so we'll be using LM Studio in our course because some of you may not be having a GPU. That's why we'll be using LM Studio. So similarly, Olama is also there. Olama has a relatively simple setup. It supports CPU and NVIDIA CPU. It has a very good support for NVIDIA GPU, and for AMD GPU only some AMD GPUs are supported. There is also VLLM. VLLM is a production grade service, so it handles heavy workload very well. Olama and LM Studio don't handle like multiple requests or heavy workload. In this case, VLLM is used. VLLM is mainly used in if you are hosting a LLM for company or out server use. Will not be using VLLM in our course because it setting up VLLM is a bit difficult, and also it is best supported on NVIDIA GPU. Even on CPU, it's not like properly supported, so we'll not be using VLLM. And what open source models will are there? So Qwen 3 is a great general purpose model. It provides us with better tool calling, thinking, then structured output. Gamma from Google is also a good language model. Then GPT OSS from OpenAI is also a good model, but it is a relatively like bigger model, like 20 billion parameter model. A Gamma and Qwen 3 models are like 4 billion, 3 billion parameter model, which we can set up on our laptops. Then there's also Llama family from Meta. Then there is Phi models from Microsoft. So how we can set up LM Studio? So first we have to go to LM Studio website. From here you can download the software for your operating system for Linux, Windows or Mac OS. Then after you have installed LM Studio, you can open LM Studio. So here you can search for various models. Uh, the model that I best recommend for testing purposes, if you are using, which is the Quen 3 4 billion. As it is a 4 billion model, I think it will be best supported on all your laptops because it only takes about 2.5 to 3 gigabytes of RAM. Everyone will have at least 8 GB or 16 GB laptop, so this model will be supported by most of you. It has two variants. It's the thinking variant and a normal variant. So thinking variant provides with the like thinking, deep thinking, and the normal variant only supports tool calling. So both are, you can download both or you can just download one. We'll be using a normal variant for our session course. So you can download it and then run in the chat. You can try using it. So here it provides us with a parameters to load. So context length, you have to define the context length for the model. By default, the context length will be like 4,000 tokens. Now 4,000 tokens isn't a lot when you're building AI agent. For AI agents, you need at least 16,000 tokens to get proper context. So you have to do increase the context length to 16,000 or more. But do keep in mind that increasing the context length will increase your memory usage. So increase it accordingly. Then it also has some like GPU offload, which I've not enabled my GPU here. You can go in the settings page. There you will see hardware. And in runtime, you can see what runtimes are supported by your current system. I have now supported like Llama CPP via CPU and Vulkan, that is the GPU acceleration. Here I can select my engine. I want the Vulkan engine, so I will select the Vulkan engine. It is the GPU. Then you'll get the option for the GPU here. Then you can load the model, Quen 3 4 billion. So the model has like 36 layers, the 36 transformer layers. So you can choose how many layers to load on the GPU and CPU. If you can load all the models on the CPU or all the models on the GPU, don't try to do like some models on the CPU and some on the GPU because it will take up the memory bandwidth and the output response will be very slow. So either put all the layers on the GPU or all on the CPU. So then you can load the model. I have now loading all the layers on the GPU. So it will load the model. Then you can try chatting with it. LM Studio provides a proper UI where you can chat with it. It also provides us with some basic tools like JavaScript Core Sandbox. Then there is RAG. Also provides us with MCP, which I will deep dive into later. For now, you just have to understand that it can take multiple tools. So this is a UI through which you can test it. Now, how can we access it via an API? Because we'll not be using this UI for AI agent. So LM Studio provides the developer section. In developer section, you can create an API server which exposes the model via the chat completions API. You can see post v1 chat completions API. We can use this API to connect with our model, and you can see that it is reachable at 192.168, which is the IP of my system. In setting, you can see in settings that you can define a custom port, cross origin resource sharing. You can enable or disable that. You can check if you want to serve on the local network or just on your laptop only. You can change that. So there are many options here. You can try those. So now how to connect this model via the API. So you can see it gave us the response. You can check the developer logs here. It will provide you with logs, received request, generated prediction. So you can check the logs if you need to debug or check anything. So you can use LM Studio to connect with local models and run them on your local machine. So where is this local LM useful? As you know, if you are doing like production grade systems, you need to use paid models because free models are not that useful. Now for that purpose, you cannot do a testing on the paid models because it will just consume all your token. For that, while testing, you can check using local models. If our system is working fine, then we'll go on to the paid model. So it provides us with a good testing base that we can use here. Okay, so now the core part. What are AI agents? So AI agents are nothing but it consists of an LLM. It uses tools. It has a memory for its previous history check and a context like documents or uh, web search tool, so it can get context. Now AI agents are of two types. There are the static agents and dynamic agents. Now static agents are known as workflows because in that you have a predefined workflow. The part of the agent is only to craft a response. Like if you have an agent for like generating a document, generating a poem. So all our workflow is set. We just have to provide as a topic, give a few context, and then it will generate the poem or the story. So this is like a static agent or workflow. Then there are dynamic agents. So dynamic agents, what they do is they define their own path. They select which path to go. But they don't have a predefined workflow. They are dynamic in this case. So the LLM itself decide based on the query which response to take, which output to take. So AI agents are dynamic, whereas workflows are static. So how can we build these AI agents? So for this purpose, there are various frameworks: LangGraph, Crew AI, then OpenAI Agent SDK. If you encounter any problem, you can go and check their documentations. Their documentations are very good. You can understand almost 99% of the knowledge about AI agent, their frameworks. You can get from these framework documentations only. So what these frameworks enable us to do is they simplify our work. They have some optimizations. Has pre-built templates for messages, tool usage. So this make us easy to build applications, AI agent applications. So we are using frameworks. We can also use the vanilla OpenAI client to build our agent, but for that we need to write a lot of boilerplate code, which makes development a bit difficult. But if you have a like simple AI agent or a workflow, you can use the directly OpenAI client because it will make your work a little bit easier if you don't know a lot about the framework. Because the frameworks, they provide us with the abstraction, but while they provide us with the abstraction, they also hide a lot of details behind the scenes. They don't provide us with how they work underneath. So if you are not clear about their process, you can just use OpenAI client, because using OpenAI client, everything is visible to you. So you know what exact prompt you are giving, what tool you are calling. So you don't have to rely on like guesswork if you don't know the framework implementation in the detail. So for that, you can use OpenAI client. Using framework also has some disadvantages like I talked about. It hides the underlying prompts and LLM calls. You can't debug it easily. It makes it harder to debug. And while creating simple workflows, it will make our job complex, because while it introduces abstraction, it also makes a bit difficult to build something small agent you have to build. So at that time it can be a bit complex using framework, which can be easier using just the simple OpenAI client. So now in this course we'll be using LangGraph as the SDK for our learning purposes. So why LangGraph? So LangGraph is an agent SDK that uses graph flow execution. So in this we are defining our agent using nodes and edges, and the agent will follow the predefined or the dynamic edges and execute according to the flow. Uh, because here we can get a lot of control and define the exact flow. Uh, Whereas Crew AI SDK that I talked about, it doesn't give us like the multiple flows. It only has like the hierarchical flow and the linear flow. Like linear flow means it goes from one node to next in a linear way, and hierarchical means it uses in master LLM to determine which path to go. Whereas in LangGraph, we can use a master LLM to define our paths, or we can manually define our path. So it gives us a lot of control, which is not provided by tools like Crew AI. So data processing or the text generation is done by the nodes in LangGraph, and the flow is decided using the edges. LangGraph provides us with a both functional and graph API. A functional API is a bit difficult to use, whereas graph API is very simple to use. So we'll be using graph API. Now the state, the agent state, that is like the memory of the agent, is defined using a typed dictionary. So to get the input and output state of the nodes, we'll be using type dict to define the state of the node. So what does a node do? A node takes the state as an input and returns the JSON output with the keys of the state. So as you can see here, we define the agent state for a simple sentiment classifying agent. For that, it takes the input sentence, then the LLM classifies the sentiment as positive, negative, or neutral, and then it provides us with the score. While defining type dict, what you have to remember is that you have to always provide it with a strictly type hints, strict type hints, like sentence, its data type is string. A sentiment, its data type is generally string, but we only require like positive, negative, or neutral. So it only has the three options. So we are providing it with literal. So it will only output in positive, negative, or neutral. Then score, the score will be in floating point value. So we are going data point as float. So then we defined our agent here. So the graph is defined using state graph from LangGraph. It takes the agent state as the argument. Then we are adding the node to get the sentiment. In this is a node. So what the node takes is the state as an input. Then it calls the LLM. So it gives us the calculate the sentiment of this sentence. Then it returns the sentiment and the score as a dictionary. So the LangGraph uses the dictionary output to update its state. So you have to always return dictionary from a node. If there is no, the LLM is not providing any output, then you can return an empty dictionary. But always you have to return a dictionary, be it empty or the outputs. Then there is an edge. So a graph always has a starting point. So from start it goes to get sentiment. Then we are adding a conditional edge. So what a conditional edge is that it every time it doesn't go to a predefined node, but it has multiple options, and based on the condition satisfied, it only goes to that node. So we define a conditional edges route. So it routes to like a positive sentiment, negative sentiment, or a neutral sentiment node based on the sentiment. Like if the sentiment is positive, it goes to positive sentiment. And this positive, negative, and neutral sentiment are nothing but simple nodes for demonstration purposes. What they do is they just print the result, like the sentence is negative with a score. This is just for demo purposes. And as I said before, if there is no output, then you have to return an empty dictionary. So then you have to define the endpoint. Like after the positive sentiment node is called, you have to finish it because there is no next node. Then you have to compile the graph. So for that, we just have to call graph.compile. Then you can call the agent using agent.invoke and use the dictionary to call it. Like I said, everything in LangChain and LangGraph, it's based on the runnable base class, and it exposes us with an invoke method. An invoke method takes a dictionary as an argument. So we'll try running this code and see what it outputs. Ensure the spellings are correct, otherwise it won't work. So the result, that is the output from the agent, is nothing but the state that we defined here. So we'll get the agent state as an output. We can see I gave it an input of I had a very boring day at college. We called the negative node. You can see it printed the sentence with a negative of score 0.9, and then the result, which is the agent state as it is. So what you have to take care while building agents. The most important thing is to properly define our input and output states using proper uh, strict type-ins. Then use proper tools, use proper output, structured outputs, and properly define the context. So I guess that makes it a better agent. Just providing the agent with a proper context and tools will take your basic agent into a like proper fully functional agent. So what structure you have to define for creating agents? The LangGraph has provided us with an structure. So in our my app structure or the project structure directory, you have to create a my agent directory. Under the my agent directory, you have to put all the tools, the nodes, and the state in the utils directory, and define the agent under my agent directory. In the main directory, you have to provide the pyproject.toml, which is automatically created when you use UV. and the langgraph.json, which defines the configuration file for the graph. So we'll be looking at this later. For now, we'll just use a simple one file or two file structure. Now, what are the components of an AI agent? So as I said before, AI agent consists of an LLM, memory, tools, and context. These all the four components are necessary for a proper AI agent to function properly. A good LLM provides with a proper reasoning, the text understanding, and it makes proper decision. Um, Setting a good memory, like you have to optimize the memory usage, because as I said before, LLM doesn't have a lot of context, especially local LLMs. Local LLMs can max go up to like 100k or 200k context limit. The highest memory for LLMs is like Google Gemini, which has like 10 million token limit. So you have to ensure how to keep our memory in the limit. If the memory like goes out of bound, we have to summarize the memory, which is actually used by Anthropic Claude code. Claude code, what it does is, if your chat history goes up to beyond a certain limit, it tries to compress it, that it condenses the chat summary. If you provided like some unnecessary queries, some wrong responses, it deletes that and only takes what's necessary to preserve the context. Then excellent tools provide with a view the LLM proper capabilities. So proper tools are necessary while building agents. Also context. Context includes the system instruction, the documents, and user query. So this is the theory for today. Now we'll build a simple agent in today's session. The agent will be two. This is like a Gantt chart. So we'll be using our LLM to give it a project idea, then set a project timeline, and it will automatically generate the Gantt chart for us. We don't have to do anything. We don't have to set the color chart, or it will automatically do it for us. So how is this done? So for that, I have defined a simple function, Gantt chart generator. So it takes a project data, which contains the timeline for the task, the start and the duration of the each task, and then it uses the standard matplotlib library in Python to generate us the Gantt chart. So this is the code for creating Gantt chart. As I said before, in production environments, logging is very important. For that, I have defined a logging handler. So it's gives us a basic idea about logs, what the agent is doing currently. Like it says generating Gantt chart successfully generated, Gantt chart saved to the path, and if an error is encountered, then a certain error was there. So this is the main entry point of our agent. So in that I've defined a system message for it. Like you are a Gantt chart timeline generator. You will be given the project idea and the total time in which to complete the entire project. Then based on that, you have to break down the project into tasks and assign each task a start week and a reasonable duration. And after that, I gave it a prompt that generated 30-week project timeline for building a web application. Now here I am not using any tools because, as I said, it's a very simple agent. It doesn't need any tool. Just structured outputs will be enough. So many a times you will face the problem like, should I use tool? Should I use structured output? So if you are not clear, first don't use any tools. Just try using structured outputs, because while using tools gives our agent a bit more power, it also consumes our input tokens. So it's better to first try with just using basic structured output. So I'll first run this code. As you can see here, we get the logs, and this is the timeline that the agent created for us. Now we can check the output it gave us. So you can see I gave it a 30-week timeline, so it's there in the constraint. So it only provided us with the 30-week timeline project. So this type of you can build this type of simple agents to simplify your workflow. I created this agent to create Gantt charts for my major project creation. So similarly, you can try building simple agents to automate your workflows. So you will see that I didn't use LangGraph here because it's not necessary. We are not using any complex workflows or any complex states. So we don't need any agent framework. Simple LangChain is sufficient for that. If you want, I will use LangGraph to implement this. So do you want me to implement this in LangGraph so that you can get an idea how to use LangGraph? So the next session we'll be using LangGraph to build complex agent. So now if you want a brief idea about how to build using LangGraph, I can give you an idea. So do you want me to implement in LangGraph? Just type yes or no in the messages. Okay. So I will show you how to implement this in LangGraph. So the most important thing what you have to import is the state of the agent, state graph, start and end. Start and end are basically constants which point to a string. You can check it. So the start is like underscore underscore start, and end is underscore underscore start. You can also type that, but you can also use it from the constants provided by the LangGraph library. Constants, using constants is better because if anytime in the future if these definitions change, we don't need to take care of that. Then to define the state, we'll be importing type date from typing type dictionary. Then we'll define the state of the agent. Now, what input it should take. For creating a Gantt chart, it will take first the project idea. So I define project idea. The data type of project should be string. Then time limit will be the number of weeks, the integer data type. Then the messages for our AI agent. Messages will be a data type of list. So you can just use list, or if you want to be more specific, you can use the base message class. If you want to be like strict type, so you can from langchain core dot messages import base message. So all those AI message, human message, system message, they are inherited from the base message. Then what the agent needs is the project data structured output. We can directly define the project data here, or we can just define it in our node. So I guess it will be easier to just do it in node, because if we do it here, it will be the agent state will get more complex. Instead of that, I'll just define it in the node itself. So now we have to get the graph. So when you define agent state, what it does is the state graph takes the state schema, context schema, input and output schema. So input schema is what the schema defined what the agent takes as an input. The output schema is what the agent provides as an output. So if you just provide it with a single agent state, it will put all the state schema, input schema and output schema as the only agent state. The state schema is the schema defined for the nodes. Input is for the input for the agent, and output is the output of the agent. You can define different state schemas for each of these states, or you can just use one state. Now we'll define our node for to generate the Gantt chart. So it will take the input of state, and it will be agent state. Now I will get project idea from the state, time limit from the state. Then there is no messages because this is the first node in the agent. There will be no message history. So we'll define an empty messages. In this we'll define the system instructions, system message. So I'll reuse the same. So this is I will define the timeline here. Define the project idea. Then for the LLM, and I'll define the node. Then I'll set the entry point from start by adding the edge from start to generate Gantt chart. Then I'll finish the workflow and I'll compile the agent. Now this will use structured output to get the timeline with structured output. For structured output, there is the project data. We're defining those here. We're using Pydantic to define the structured output format. I'll validate the response just in case if there's anything wrong. There's no typo here. Ensure that while creating agent, you don't get any typos here, because if you get any typo mistakes, it will fail to work. So ensure the names are consistent, especially the node names and the edge that you define, because the LSP will not give you the correction for that because it doesn't understand data in quotes. Now we'll pass this response to our tool, which is the generate Gantt chart. Operating. For generating Gantt chart, I'll be importing the required library. Then after that, uh, I will just return the messages to update it into the state. So this is our basic agent code. Now I'll try to run this agent and see if it works. So as an agent is also a class derived from the base class runnable, it will also implement the invoke method. Here we have to give the basic idea. So the project idea, it is a simple web application. Time limit is for 30 weeks and change it to like 12 weeks. A web page for typing. So now I'll run this. So print the result for you to see how the state updates. You can see the Gantt chart was saved. The messages that we updated in the our node, and this is what we provided to the agent as input. Now we'll see what Gantt chart it created. So yeah, you can see it created a not exactly perfect but a functional Gantt chart. If you want to make it better, you can like provide the tasks, uh, what custom tasks you have, then it will give you a proper response. So now I'll go through the code again if anyone has missed the code. So what we did we imported state graph from langgraph.graph. We used typedict to define our state schemas. We imported base messages, human message to define the messages key. Then imported the env values, used OS to get the model and base URL. Then we used chat OpenAI, used pydantic to define a structured output format, matplotlib and pandas to generate our Gantt chart, defined our language model here. We defined the state of the agent with strict type hints, string, integer, and list. Then we defined the structured output format for the LLM, the project timeline, and the project data using pydantic. We used field to provide it with a proper description, name of the task, what it actually means. Start means the start week of the task, duration, the duration in weeks of the task. Because providing proper description makes the model understand what to give output. It provides proper output. It understands the exact information to provide rather than guessing. Now we define the generate Gantt chart function here and uses just simple matplotlib. You can go through this code, or this was given by ChatGPT, so you can use ChatGPT for like getting your tools if you are um, it's difficult to provide you with the tool code. You can use ChatGPT or any other AI to get the code for your tools. Then this is the generate Gantt chart node. It takes the agent state as an input. Then from the state, it gets the project idea and time limit keys that we provide as an input when running it. Then we defined our messages. We gave it a system instruction. So what you are, what job you have to do. Then we gave it a human prompt like to generate a project in the given timeline for this idea. Then we got the structured response from the LLM. We validated the response to check if there were any error or not. Uh, while doing this in production, I would recommend using try and except because you are calling an LLM and the LLM service may be down. So it's better to do it in try catch and use proper logging. Then we call the generate Gantt chart function and return the messages as a state update to the agent. Then we defined our graph. We added nodes to the graph. We defined our workflow using edges. Then we compiled our graph. If you want, you can also see what your Gantt chart looks like. You can just call print Gantt chart. So this is like getGraph.drawASCII. You can use this method to print the Gantt chart. If you're using like Jupyter Notebook or Google Colab, when you run graph.compile, it will show you an image of the graph. So I'm using in terminal, so I'm using printing it using ASCII. So you can see here they provided us with the workflow, how it starts, goes to the generate Gantt chart, and ends at the end. Logging, the basic Python library logging, because logging is also a very good library which you can use. So for that you just need to import logging. Then you have to set the logger. You can define the name. Then you have to set the logging level. We'll explain this in a few minutes what it does. Then you have to set up the handlers. Then I'll use logging here. So I'll use this iterate try except block. Now if you run it, you will see logs like it's called the Gantt chart node. Then invoke the LLM, and LLM responded successfully. Called the generate Gantt chart function and generated the Gantt chart and saved it. So how to use the logging library? First, you have to import the logging library from Python. It is a standard library. Then we have to set the logger name. You can set it any custom name, or you can define it as the main, like anything will do. Then we have to set the level. So what does this level do? So there are different logging levels, like the not set, which is by default, it is no level has been set. Then debug, info, warning, error, critical. So when we set the level as debug, what it does is it filters the messages so that the messages with the level of debug or above, that is debug, info, warning, will be seen. The messages below that will not be seen because I set it as debug. All the messages above will be seen. If you set it to info, what it will do is it will only provide you with like info and warning, critical errors. It will not provide you with the debug information. The best practice is to do what? You have to set two handlers. The first handler is for like the streaming handler. The streaming handler outputs the logging information onto the terminal, and the second handler used to say handle it using the file. So you have to log the data in the file. So I will implement this here as well. So this is the first handler which gives us on the terminal information. Then there is a second handler. The logs will include everything from debug, whereas the stream handler, that is the terminal, will only provide us with the information about info and error. We've added the log handler to the logger. Then when we call this logger.debug, so what it does is it sets this message as a debug message. So when I call this, it will first go to the logger set level. So it's a debug. So then it will pass it to the handler. So now you can see the stream handler, it's a terminal handler, only has like filtered at info. So our message of debug, which has a lower priority than info. So everything below info will be discarded. So this message will not be seen on our terminal, but it will be seen on our file. It will be get saved on the log file because we have set the level as debug. So it will be saved onto the log file. So in this way you can set debug, error and other level. So now you can see only info message was there because the user only needs to know that the Gantt chart was successfully created and saved to chart.png. He doesn't need to know that a call was made to the LLM or this specific node was called. The end user doesn't need to know that. But if something goes wrong, you can check the logs. So in here you can see it gives us the debug and info. All the information